In this lesson, we're going to talk about a method called completing the square. And this is a method for solving quadratic equations. So first, let's kind of dive into this idea of a square and why it needs to be completed. So what if we got an equation that has no x term, and so we can't use the principle of square roots. So what is that principle of square roots? Let's remind ourselves of that. So if we have something like the principle of square roots would apply to something like this. If we have 2x squared equals 10, we could divide both sides by 2, and we can get x squared equals 5, and we can square root. And we get two answers. X is positive or negative square root of 5. All right, so that's using the principle of square roots. And that works nice when we don't have an x term. We just have an x squared. Well, when we have an equation that has an x term, well, we can use this method called completing the square. All right, let's think about this square over here. And let's think about its area. All right, we want to describe the total area enclosed in this square. All right, so if we remember, the area for a rectangle is length times width, and for a square, the length and width is the same. So the area formula for a square is the area equals side times side, or area equals side squared. All right. So whatever this length is here times itself, because it's the same thing, all right? So, well, what is this length here? This is x. X is the distance from here to here, okay? And so the whole distance here would be x, and then this little distance is 3 right there, so we're going to add on 3. So x plus 3 is the length of this side. I don't know what x is, but whatever that length is, this whole thing is x plus 3. And the height here is also going to be x plus 3. All right, so the area of this square can be written looking at the length and the width, which are the same. We can write it as x plus 3 squared. So that's one way we could find the area of the whole thing. Or we could find the area of the pieces. Let's go ahead and find the area of the pieces. Look at this light blue rectangle here. It is x wide and x tall. All right, so the area of this piece would be x times x, or x squared. How about this piece over here? It's a rectangle. It's 3 wide and x tall, so this has an area of 3x. And over here, this other green rectangle here has a height of 3, and the width, which is the same as this, the width is x. All right, so that's 3x also. And then last, we got this little reddish piece down here. It's 3 by 3 because this length is 3 here, so this length is 3 down here, and 3 times 3 is 9. So we could say the area, the total shaded area there, is all of these pieces added up. That's x squared plus 3x plus 3x plus 9. Okay, now we're gonna have some names for this. We're gonna call this one up above factored form. All right, so that's our factored form. We'll call this expanded form because it's kind of written all out. And then if we wanted to simplify this, we can get the simplified version, and we can combine like terms, the 3x plus 3x, and we can write it as x squared plus 6x plus 9. Now, all of these three expressions represent the area of the shaded region over here. So they're all equivalent because they all represent the same thing. So this is just a nice way to prove that we have x plus 3 squared is x squared plus 6x plus 9. And we've talked about that a little bit in the last few lessons. Remember, it's not just x squared plus 9. Don't just go squaring these. There's that 6x, and this is y. All right, so let's use this a bit. So here we have some squares, and we want to write the area in factored, expanded, and simplified form. All right? So, first of all, factored form. That just means let's look at this whole thing. That's x plus 5. This is x plus 5 here. And so, factored, the area is x plus 5 times x plus 5, or x plus 5 squared. Now, if we want this in expanded form, in other words, we want to multiply it all out, then we just get the different pieces. And this little piece is x squared. This piece here is 5 by x, so it's going to be 5x. And this one's also going to be 5x. And this little piece over here is 5 by 5, so that one's going to be 25. Right? So our expanded form would be all those pieces, x squared plus 5x plus 5x plus 25. And then last but not least, simplified. All right, we get x squared plus 10x plus 25. And again, all three of these are equivalents, right? So there's our simplified version. The area here can be represented by x squared plus 10x plus 9. All right, let's try one more like this. Now a little difference here. If we have, in this case, we got a minus. Now, can you really have a negative length? No, you can't. But this is a model. And so the model is not perfect, but it does help us to kind of understand what's going on. So this is going to be x minus 7 squared. All right, so that we'll call that our factored version is x minus 7 wide and x minus 7 tall. So that's x minus 7 squared. Okay, that's our factored version. So the simplified version, this piece is x squared. This piece here is negative 7 by x. Again, that's kind of weird with the negative, I know. But yeah, let's go with it. Negative 7x, negative 7x. And what's the area of this little piece down here? Well, since this is negative 7, this would be negative 7 tall, negative 7 wide, and negative 7 times negative 7 is 49. So our expanded would be all those pieces added up. So x squared minus 7x minus 7x plus 49. And last but not least, our simplified, if we combine like terms, we get x squared minus 14x plus 49. All right, great. So we have these three versions. They're all the same. Okay, and we want to kind of look carefully, especially at this simplified version. Okay, so look carefully at this simplified version, and we'll compare that to the factored version. All right, and we've seen some things here. So where does that 49 come from? It's that 7 squared. Where does this, what's the relationship between this negative 14 and that negative 7? Well, this is half of this, right? Kind of goes with that whole 2ab that you maybe have remembered from that a plus b squared formula. All right, so what's going on here? What's the relationship between the 5 and the 25? Well, this is squared. And what's the relationship between the 5 and the 10x? Well, 5 is half of 10x, or 10x is doubled of the 5 times x. All right, so there's our relationship. So now let's see how we can use that to do something called completing the square. So what if we have a square that is not complete, if it's missing some area? Well, let's look at these shapes here, and we want to find their area and write an expression for it. We're going to write an expanded form, and then we're going to decide what is the area we need to kind of fill in that gap. So here we've got this situation, all right? We've got, here we've got an x squared, we've got a 4x, we've got a 4x, and that's it. So the current area here is x squared plus 8x. Well, what is missing? What do we wish we'd have down here in order to say that this is a full perfect square? Well, we wish it was 4 by 4, right? We wish it was 4 times 4, so we need a little square that has an area of 16. If we did, then we'd have a perfect square trinomial. That's x squared plus 8x plus 16. And that can factor, because this is a perfect square. The square root of 16 is 4. And we notice that if we take 4 and double it, we get 8. So this is equal to that. All right. So it's a perfect square. It's an x plus 4 by x plus 4 squared. Great. Well, what if we had some fractions? Uh-oh. Time for some fraction action. All right, what do we got here? Here we have x squared. Here we have 7 halves x. And over here we have 7 halves times x. Again, we're missing some. So what we have, though, is we have x squared. And then we have 7 halves plus 7 halves. And if we do a little fraction arithmetic, that's 14 halves. That is 7 halves. 7 halves plus 7 halves is 7 wholes, right? So the area we have is x squared plus 7x. A nice neat 7 there. What are you missing? What do we wish we had if we could fill this in? Well, this little square here is 7 halves by 7 halves. So 7 halves times 7 halves is 49 fourths. So this would be 49 fourths. So the missing area that we wish we had was 49 fourths. And if we had that area, then the whole thing would be x squared plus 7x plus 49 fourths. Kind of ugly there with that fraction, but that's what it would be, right? And this could be factored, the whole square now. We've got a square here. So this whole square could be represented by this expression here. And this square is just an x plus 7 halves by x plus 7 halves. So it is x plus 7 halves squared. All right? 7 halves squared is 49 fourths. 7 halves doubled is 7. So there's a relationship here. So what's this piece that we need to add? Well, to generalize here, if we start with something like x squared plus 7x or x squared plus 8x, what is the thing we need to add? Well, this is 6, which was half of this 8, 4 squared. Here we added 49 fourths. That's half of this 7 squared. So the rule that we need to remember and understand is that if we want to complete the square for something that looks like x plus bx, like this, x plus 8x or x squared plus 7x. So x squared plus bx. To complete the square and to make it so that we can factor it, we need to add half of b squared. All right, this is what we need to remember. Half of 7 is 7 halves squared. Half of 8 is 4 squared. Okay, so how this helps is that when we complete the square, we can factor. So if we can complete the square, then we can factor one side, and then we can use the principle of square roots.